Hi, this is Engineer Ahmed again. In this lecture, we'll discuss valve flow coefficient or valve capacity. So, how to decide the capacity of the valve? Capacity means not only flow, also differential pressure. So, we have to find out a parameter which represents the capacity of the valve. So that coefficient is a valve flow coefficient CV. So CV is a nothing but that depends on relationship between flow and the differential pressure divided by specific gravity. So like any flow component, valve principle is also depending on flow and the differential pressure across it. So what is differential pressure? So inlet pressure and difference of inlet pressure and the outlet pressure. So depending on this, flow is proportional to square root of dP square root by g. If you remove the proportionality, there is a constant you have to put. That constant is called the CV, valve coefficient, valve flow coefficient. So this is an important parameter which represents the capacity of the valve. If we solve for the valve coefficient CV is equal to Q square root of G by differential pressure. So it depends directly on the flow and inversely on the square root of differential pressure. So CV represents the capacity of the valve. So because practically you will have many applications in process industry, many different flow conditions, differential pressure conditions, different types of fluids. So you cannot, for valve manufacturer cannot design for each application. So if you go to the valve vendor, he will ask for your CV, process CV. So that can be calculated by using the maximum flow and dP and specific gravity of the liquid type, that is type of liquid. So you calculate the CV, you go to the vendor or manufacturer of the valve, he will provide a suitable valve with that particular CV, slightly higher CV valve he will provide. So that will suffice for your flow application. So that was the philosophy of flow coefficient. So we'll see what are the definitions of Q is the liquid flow rate in GPM, gallons per minute. So this is for liquid applications. CV is the flow coefficient that describes the flow capacity of a valve. As I told you, flow capacity is represented by CV, flow coefficient. Delta P, that is pressure drop or differential pressure or whatever you call this, P1 minus P2 across the valve in PSID. PSID, because it's a differential pressure, we will write a PSID. So G is the specific gravity of the fluid at the valve inlet. Specific gravity represents the type of fluid, so how it is density with respect to the water. So G represents the type of fluid. So it is a specific gravity of the fluid which is available in the tables of the valve. So with this we will solve for the CV using a software. Nowadays softwares are available. So with that software we will go with a vendor or manufacturer to get a suitable valve. So that how this CV depends on what are the parameters we will see next. Now we will see what are the determinants of CV, which are the parameters, which are the factors deciding the CV. CV is directly related to the percentage of travel, valve travel. So After calculating the CV, you should decide you will get the area, seat area, and with that area and percentage of travel, so you have to decide the type of the wall and the size of the wall. CV is greatly influenced by wall internal geometry. So internal geometry also important. That is a type of plug, type of cage. So shape of the cage, it depends on the CV. Influence it will influence the CV. CV is determined by vendors using a lab test. So CV is found practically by using as we discussed in previous definition of CV, by allowing a suitable flow and maintaining 1 psit pressure across the valve of a water, they can find out the CV. So that is a practical CV. CV test is done on relatively small sizes and interpolated to larger ones. So because of practical problems, vendors cannot do for all types of valves because there is not huge flows they cannot create in their workshop or in fabrication units. So they will do it for small sizes and interpolated for larger ones. So that is a normal practice. So CV determines the above factors: wall travel, internal geometry, and the practical elaborate determination of CV in the lab tests, and CV test done on relatively small sizes and interpolated for larger ones. So that is the determinants of CV. Now in this slide we will discuss about the pressure drop ratings. So there is a flowing conditions and there is a shut-off conditions. Flowing conditions means there is a minimum flow, there is a normal flow, there is a maximum flow. Shut-off pressure means fully closed, valve is fully shut. That is extreme condition. That is a shut-off pressure drops. So what is a pressure drop in different conditions? So like any flow element, across control valve, as flow changes, differential pressure also changes. So the flowing pressure drop refers to the difference between the upstream pressure P1 and the downstream pressure P2 while the valve is throttling. Valve throttling means it may be any position between minimum and maximum conditions. So the difference will be changing. So how it will change we will see in the next throttling. So the shut-off pressure is a pressure drop is the difference between upstream and downstream pressure when the valve is fully closed or fully shut. So shut-off pressure is always the worst dP across the valve. Worst dP means this is a maximum condition used for the sizing the actuators. So shut-off pressure is used for the design of the actuator, because at the worst condition the actuator should be able to open the valve and close the valve. So for designing, this dP will be taken into consideration. That we will see in the software operation and sizing of the valve and the actuator. Next. Now in this slide we will see how the pressure drops are. Pressure drop is there in flowing conditions and shut-off conditions, pressure drops. So this is a flowing condition. So flow may be anywhere between 0 to 100%. So inlet pressure is 500 psig, PE2 maybe 450. Flowing pressure drop is 50 psid. So this is a difference between these two. So this is a normal example for a flowing conditions. So this also vary depending on the valve opening and the amount of flow passing through the valve. So in the shut-off, it is fully shut valve, and P1 inlet pressure 500, P2 is almost 0. We are assuming that this inlet pressure is coming from the reservoir, from the underground in oil and gas conditions, gas wells, and outlet side there is no pressure. So there is a shut-off drop. Shut-off pressure drop is 500 psi, which is extremely high. This extreme high pressure happens, it's a worst condition. So in this condition, your actuator has to start opening the valve. So that takes a maximum torque or force required by the actuator. So that's why this shut-off pressure drop is used for sizing the actuators. So this flowing pressure drop is used for sizing the valve, so that we will have three conditions: minimum, maximum, normal, and maximum conditions. That we'll see in the next in example how this pressure drop changes in three conditions. So for sizing we'll use at least three conditions. So for sizing the valve, that we'll see in the software operation. Now in this slide we'll assume three conditions and what are the flow conditions and the differential pressure drop, and these conditions we'll use in the sizing of the valve using the software, that we'll see next. So in this flow and pressure drop across the control valve, as we have seen, pressure drop will vary with the flow and also with the, of course, with the valve travel. So here we are seeing the valve travel percentage and flow through that, at that valve travel, inlet pressure, outlet pressure, and differential pressure. So at minimum condition, that is assumed as 10% of valve travel. 10% of valve travel is assumed for the minimum conditions, and at that time flow is maybe 100 GPM, that is Q. Inlet pressure we are assuming constant 100 psig, maybe it is coming from the reservoir of oil reservoir, that is P1. Outlet pressure will vary according to the valve travel and the flow through it. So here in this condition, minimum conditions, we assume that outlet pressure is 20. So what is a differential? 80 psid. So this is a differential pressure, that is a delta P or dP. So first we will discuss maximum condition. Maximum condition happens at, assumes to be at 90%. So 90% maximum flow may be 500 gallons per minute. So inlet pressure is 100, outlet pressure is 80, because it valve is 90% open and slowly pressure is developing at the outlet side. So that is assumed to be 80. So in this condition, what is the differential? It's a 20 dP, 20 psid. So normal condition is a normal condition in between minimum and maximum. So normal means 50%. So flow is also nearly 50% of these two, that is 300 GPM. Inlet pressure assumes to be constant, and outlet pressure is again the middle of these two. So differential pressure is also middle, that is 40 psid. So shut-off pressure, as we discussed, shut-off means a fully closed valve, 0% open or full close. So during that time, flow is assumed to be 0, no flow at all, and inlet pressure is same. Outlet pressure is 0 because there is no outlet side pressure. So differential is maximum 100 psi. T, as we discussed earlier, it is a worst case differential pressure. This is used for the sizing of the actuator. because when it is fully closed, it has to apply maximum torque, force or torque to open the valve from that position and throttle it as per the required position as per the command of the controller. So that we'll discuss later. So these are the examples of this minimum, normal, maximum conditions and shut-off conditions. So this data we'll use in the software, sizing software example, so that we can calculate a CV of the valve using the software. So that operation we'll see next.